Good morning class and welcome to our continuing discussions on hydropower technology. Today we will give an example of the largest hydroelectric power plant in the world, the Three Gorges Dam in China, and look at some of its characteristic features. So the Three Gorges Dam, which is located in the Yangtze River in the Hubei province of China, is currently the world's largest hydroelectric installation. It was completed in 2012 and the dam is 2,335 meters long and rises 181 meters above the riverbed. So the total height above the riverbed is around 181 meters and it's a huge dam whose length is around 2,335 meters, over 2 kilometers in length. So the normal level of water in the dam is 170 meters above the low level flow. So what is the general flow of the river? The reservoir that is created by the dam, that reservoir, the height of water on the reservoir is 170 meters above the flow downstream. Okay. So the total height then you are getting is around 170 meters. The catchment area is around 1 million square kilometer here. So this is the total catchment area over which this the river of this dam is collecting water from, and it extends 600 kilometer upstream, and the total surface area of the reservoir is 1000 kilometers square. So you can understand the sheer size of the reservoir that has been created for this for the purpose of this hydroelectric power plant. In this dam, there are 32 Francis turbines. As we discussed, Francis turbine is a type of reaction turbines that are ideal for large-scale hydroelectric power plants. 32 of them are installed in this Three Gorges Dam, each having a capacity of 700 megawatts. So at its rated power, it's 700 megawatts, 700 megajoules per second. The diameter of the turbine blade is 10 meters and the running head is 81 meters, and the maximum flow that these Francis turbines can handle is 950 meter cube per second. So over nearly 1000 meter cube second of flow it can handle, and the head of each of these turbines is around 81 meters. There is one generator per turbine, each with rated power of 700 megawatts with a voltage of 20 kilovolts, and the maximum generator electrical efficiency is 96.5%. So the conversion of mechanical power to electrical power is highly efficient, around 96.5%. So the total installed electrical capacity is 22,500 megawatts, that is 22.5 gigawatts, which is around 30% of the UK's capacity in generation, just to give an example of the scale of electricity this power plant can generate. However, the power output depends on the flow of the river, which is varying strongly with season. Okay. So output is typically around 5,000 megawatts during the dry season. So you see the capacity is 22,000 megawatts. But during the dry season, it is 1/4 of that capacity is actually getting delivered, around 5,000 megawatts, and the dry season lasts between November to May. However, during the rainy season, which is July to September, in the catchment area that we are discussing here, the power output is limited only by the plant generating capacity, which is 22.5 gigawatts. Okay. So the expected annual generation output is around 100 terawatt hours, still a very large number, which is around giving us a capacity factor of around 50%. Okay, so it has a lower capacity factor compared to the total plated capacity, primarily because half of the year it is not delivering at its rated capacity, only 1/4 of it, rest it is delivering at the rated capacity. Okay. So that is kind of gives you an example of one of the largest hydroelectric power plants and gives you that these hydropower plants can be large sources of renewable electricity generation in the world, provided that sufficiently large dams have been built and you have a river of large enough volume. So in the next section, we will discuss how to select what turbine to use where. Okay, so you will have rivers from small scale mountain rivers to gigantic rivers like Yangtze, Brahmaputra, Ganges, etc. with different available head heights. So how do you choose quantitatively which turbine to use where? Okay, and how do you choose the design of the turbine and how to convert that? Another aspect that is very important in terms of turbine design is the connection of the turbine shaft with the generator shaft, and there are important constraints there as well, as we will see. So let's look at these aspects in the next few slides. So one design parameter that is typically used in these cases is specific speed. So specific speed is an important parameter in turbine design and is defined as 0.262 times the angular speed omega in RPM, the power output W dot to the power half, so square root of the power output in kilowatts, and the head height H, water head, to the power minus 5 by 4. So it's kind of an arbitrary number, you may think of that. But this kind of a number has been developed by the hydropower engineers to specifically discuss and compare different designs of turbines and their suitability for different types of hydropower locations. So here omega is the angular speed in revolutions per minute, W dot is the output power in kilowatts, H is the water head in meters. Okay, so H will be in meter, W dot in kilowatts, omega is in RPM. 0.262 is the numerical value of the constant whose units are such that omega s becomes dimensionless. Okay, so this specific speed is actually a holdover for an earlier time where English units were used. Okay, so if we actually use the English units of H as in feet, W dot as in horsepower and foot pounds English unit of power, and omega in RPM, then the specific heat unit conversion is just omega is equals to omega into W dot to the power half into H to the power minus 5 by 4. So this is the English version from which we have created this SI version, and then we get a conversion factor of 0.262 to make this specific speed dimensionless. So it's kind of a dimensionless number helping us to select different turbine designs. Okay. So manufacturers provide the specific speed value of a turbine at their rated operating condition. So for example, in the previous example, we had the Francis turbine. Here the omega dot is 700 megawatts. So 700 into 1000 kilowatts will be the W dot for that specific Francis turbine. Similarly, its rated head is 81 meters. So this H will be 81 meters and omega is given as, let me see if the omega is given. Omega is not, there will be omega values you can get as well. Okay. So reaction turbines, so based on that you can get the specific speed. Okay. So suppose you in that Three Gorges Dam Francis turbine, the manufacturer has given the rated power output, the rated head, and the specific speed value. So you know omega s, you know W dot, you know H. Then you can find the omega or RPM of this Francis turbine, okay, for its rated power capacity. Based on that, you can find what is the speed at which the shaft is supposed to rotate, and then pair it with the generator shaft appropriately. And we will discuss an example of this in the later slide. So manufacturers typically provide the specific speed value of a turbine at their rated operating conditions where their efficiency is the highest. Reaction turbines have higher specific speeds than impulse turbines, as can be seen in the table below. So here we are looking at typical specific speed values of different types of turbines. So we have discussed two types of turbines, impulse turbines and reaction turbines. We have looked at the differences between them. Now there are multiple designs within the impulse turbines as well, which we did not go into. We discussed the Pelton turbine, but there are two other types of impulse turbines that also exist, turbo and cross flow. And you can see the specific speed range of this. Pelton turbine has the lowest specific speed value. Turbo has the highest, is somewhat higher. Cross flow is even higher. Reaction turbines typically have significantly higher specific values than impulse turbines. For example, Francis turbine, it can go from 30 to 400. So both the lower limit and the higher limit are larger than even the cross flow turbines. And Kaplan turbine is even larger specific speed values of 200 to 1000. Okay. So now, how do you use these? So suppose you have chosen, you know the head height of the river, okay, and you know the power output you need, okay, and somehow because of the generator aspect, you also know the omega value. So you can calculate the specific speed that you require for your case. Then you can look at the different turbine designs and see at what range it falls. Now there may be cases where it falls into multiple ranges. So suppose you have a specific speed of 100 you are getting, okay. So you can do both a cross flow or a Francis turbine and you can choose either of them. So that is still possible, okay. Another important part is the RPM value omega here. So how is the omega value constrained? This is constrained by the gear ratio needed to pair the generator shaft with the turbine shaft. The frequency of the AC current in North America is 60 Hz, while that in Europe or India is 50 Hz. Hertz is per second, basically revolutions per second, correct? So its units are second inverse. So what this means is the AC fluctuations is 60 revolutions per second in US, and in Europe and India it's 50 revolutions per second, the AC three-phase current waveform. Now if a generator has P magnetic poles, remember the current is generated by the rotation of the generator shaft inside a cylindrical structure which has magnetic poles in it, okay. So if the generator has P magnetic flows, like 4 poles, 5 poles, 6 pole generators, different types of generator types are available, then the required shaft speed given the AC frequency is omega shaft. This omega shaft is in RPMs equal to nu AC in Hertz into 60 into 2 by P, okay. Because this is revolutions per second, you multiply it by 60, you are getting revolutions per minute, and divided by P by 2. That's the logic here. Alright. P by 2 is number of poles divided by 2. So that's the speed at which the shaft must rotate to give the specific Hertz frequency of your AC current. So suppose your AC current is 50 Hertz. Alright. And you are using a 6 pole generator. 6 pole generator. So this is 6, this is 50. 60 by 6 is 10, so 50 into 10 into 2, so this becomes 1000 RPM, okay. So your generator shaft speed is fixed, given a 6 pole generator and your specific AC current frequency requirement, your generator shaft speed is fixed. Now clearly hydroturbine RPM will be variable, water speed may change and everything, right? So we need a gear to couple the variable turbine shaft with the fixed rotating generator shaft, okay. And we need a gear ratio good enough to deliver that 1000 RPM that we need, okay. Now typically hydroturbines have low to medium RPMs of 60 to 720 RPMs. So here again, if you see, specific speed and RPM are related. So for a given head height and a given required power output, clearly Pelton turbines, turbo turbines, etc. will have much lower turbine shaft speeds in RPMs compared to reaction turbines which have higher specific speeds, correct. So you will get lower low speed turbine shafts for impulse turbines and higher speed turbine shaft for reaction turbines. So usually therefore Pelton and other impulse turbines have low RPMs less than 200 and hence require generators with large number of magnetic poles and gearboxes to increase the speed of the generator shaft related to the turbine rotor shaft. So you have to increase the number of magnetic poles to decrease the generator shaft RPM, or you have to have a large gear ratio between the two. Okay, either of those two options. Both options increase the expense and the complexity of your installation. Okay. So in contrast, reaction turbine rotors have high shaft speeds and hence can work with less expensive generators and gearbox systems. Their submerged mode of operation also helps in easier adjustment to variable water flow rates so that AC frequency can be kept constant. Okay. So two advantages of a reaction turbine: it can generate higher turbine shaft speeds, so you require generators with less number of magnetic poles and less gear ratios, making the system less expensive. Further, because it's a submerged mode of operation, the entire system is underwater, variable water flow can be more easily adjusted, and so you do not have to invest in a expensive gearbox system controller to respond to rapid changes in water flow. That is all that will happen in an impulse turbine, where you are using a nozzle to impel the water in a rotor within a basically a air filled turbine system. Correct. Here it's a submerged system, so the changes in water flow affect the turbines less and you can control it more easily. Okay, so that makes reaction turbines like Francis turbines, like Kaplan turbines less expensive for large scale power plant systems. So reaction turbines with the ability to handle large volumes of water at moderate to low heads with requirement of less expensive gearbox systems and easier adjustments to variability of flow are a good choice for large hydropower projects. Okay. Here what we are looking at is the turbine application chart. This is kind of the engineer's chart which can help an engineer to figure out which type of turbine one should choose given certain inputs. So you know the flow that is available to you in a river system, and you know the maximum head that is available to you from the reservoir to the downstream, right? Given these two, you can identify in this plot a certain point where your likely operation in a new site is going to be. And here what we are seeing is certain ranges of operation for each of the turbine types. So this red area is the range of operation of a Pelton turbine. You can see the Pelton turbine works with high heads. This is a log plot, so it starts with around 20-meter head and goes up to 1000-meter head. Okay, so high head rivers and moderate flows, low flows. So it starts with flows of as low as 1 meter cube per second and goes up to around 30 meter cube per second of flow. Alright. Within this domain, you can choose your Pelton turbine. Okay, it's possible for you to go for a Pelton turbine. The yellow region is the Francis turbine. Okay. Now here you can also see these diagonal lines. Okay, so the power output W dot is the density of water into the volume flow rate of water into G into the total head. Correct. Ignoring the efficiencies for now. Okay. Now density of water is constant. The acceleration due to gravity is constant. So W dot is basically V dot into H. So clearly in a log plot, log W dot is log V dot plus log H. So it becomes a straight line. Okay. So for example, suppose your flow rate is 100 meter cube per second. So V dot is 100 and your height is 10 meters. So 100 into 10 becomes 1000. Okay. G is what? 9.81. So it's 10 again approximately. So this becomes 10,000. Okay. And density of water is 1000. Correct? 1000 kg per meter cube. So 10 to the power 4 into 10 to the power 3. This becomes 10 to the power 7. So 10 to the power 7 is 10 megawatts. So you can see here 10, you are getting this point 10 megawatts. So the power lines are diagonal like this going down this way. Okay. So now this is the, so then you can see the Pelton turbines can go to high power outputs, but for that you will need very high heads. So if you want to go to a 100 megawatt turbine using Pelton wheels, then your heads should better be around 500 meters or something like that. Okay, which is usually very difficult to attain. Okay, so in this context, then Francis turbines, which is the whose operational region is within this yellow quadrilateral like shape here, is much better. You can see that Francis turbines can deliver 100 meters at very low heads and high volume. So if you have a high volume river with heads as low as say 20 meters, so 20 meters and volume is like 200, 300, 400, 500, 600, then also you can get 100 megawatt power output, rated power output from a Francis turbine, which can operate at these high volumes and moderate head systems. Okay, and you can see here that Francis turbine is the only turbine that go to the highest flow rates here and goes close to 1000 megawatts. None of the other turbine types can go up to 1000 megawatts. So very large outputs you are basically going into Francis turbine region. And again here the idea is, if you go back to the Three Gorges Dam example, it's 700 megawatts, correct? So this is around here only 1000 megawatts. So here only turbine that can work is a Francis turbine. Okay, so that's why the Three Gorges Dam engineers chose the Francis turbine as their turbine of choice. Kaplan turbines work at somewhat lower in the zone, so it can go to very low heads. So you can see here Francis turbine head heights has to be 10 meters or above. Okay, but Kaplan turbines can go up to 1 meter head height. So very low heads also it can work. Okay, so if you have very low heads and reasonably good volumes, it can go to high volumes as well at moderate heads, then Kaplan turbine is the choice. Okay, so if you have heads of around 5 meters, for example, so 2, 3, 4, 5 meters here, and you want to develop a 10 megawatt turbine using a 5 meter head, then the only turbine that you can choose is a Kaplan turbine, assuming you have a reasonably good volume of around 200 meter cube per second. Okay, so that kind of distinguishes the zones. Then there are the other types of impulse turbines like turbo turbines, which kind of goes to somewhat lower heads than Pelton turbines, and cross flow, which goes to even lower heads. So these are different types of impulse turbines that can go into lower heads, but you can see all of these are constrained to below 10 megawatt levels, okay, unlike the other types. So this is what we have discussed here in the basic notes for you to understand, and this is how you can use the turbine application chart. So I will close this class quickly using giving you some of the major advantages of hydropower. Okay, it's a very well established technology. The world's first hydropower plant began operation in Wisconsin in 1882 with a capacity of 12.6 kilowatts. Okay, it was called the Vulcan Street plant and was made by the Appleton Edison Electric Light Company. So the Edison light bulb, if you remember, okay, it's one of the first. Edison was the inventor of the first light bulb. So it's a very old power company that Edison founded along with Appleton, with whom the Edison eventually merged. And the first hydropower plant began in 1882. So it's a very old and very well established technology. It can generate over a large range of scales from 20 gigawatt capacity ranges like the Three Gorges Dam to nanoscale plants that generate 100 watts of power. So you can have micro hydro turbines that can generate only one light bulb, okay, like a nanoscale plant, or you have these gigantic systems like the Three Gorges Dam. So it can scale over a very large region, okay. Has very high efficiency, over 90% efficiency of energy conversion is achievable, low maintenance, long lasting components, okay. Then a large untapped potential exists in Africa, 20 times the current installed capacity. So where is the growth in this century? Okay, Africa is a certain growth range, as we discussed originally, that there is a large amount of water resource that can still be used and is not tapped in Africa, followed by China, which is 7 times the current installed capacity, where future demand is likely to increase. Small hydro is ideal for rural and less connected areas of generating electricity for local needs. So for rural and less connected areas in mountainous villages, etc., where there is which are located close to mountain streams, you can have small hydropower plants installed that can generate electricity at the local level. Okay, so this is kind of the idea of the movie of Swadesh, if you remember. Okay, so if you look at the distributed power systems in hard to reach villages in tribal areas or other places far away from the grid, you can have a small hydro and do that. And it generates dispatchable electricity. So can be turned on and off at short notice. It's not a thermal power plant, right? You can close the gates and stop the turbines very quickly, and open the gates and turn the water flow back and start the turbines. So it can generate electricity on demand. Okay, if the demand is high, you can switch on the flow and start the hydro. If demand is low, you can stop it without significant impacts on the efficiency. Energy source is less intermittent, it is seasonal. So summer and there is a distinction between dry season and wet season, but over a certain day the energy source is not very variable, unlike wind and solar, which can change from minute to minute or hour to hour. Okay, so it's one of the few renewable resources which is not very intermittent, and hence you can deliver a constant electricity amount to the grid. Water stored in dams can be used for water supply and irrigation. So again, here one of the main advantages is that it is multi-purpose. The reservoir dam, the water stored there can be used for irrigation projects, for potable water supply. So it can do a lot of functions at once, which makes it a very good investment for many types of development projects. Okay. Hydro turbines can be made to run in reverse to move up an incline to the reservoir to store energy in times of low demand, which is called pumped hydro storage, and we will discuss this a little bit detail in the next class. How you can use hydro turbines as a way of storing energy, as an energy storage technology rather than an energy generation technology, and we will discuss this in the next class, but it's also one of the main advantages of hydropower. Okay, so I will stop here today. We will have a small class next where we will close the hydropower section. Okay. Thank you for listening and have a good day.